Hello, welcome to another video of thermodynamics. In this video, I'm going to explain how to find the entropy change of ideal gases using TDS relations. So we learned two TDS relations, TDS equals du plus p dv, and we also learned that TDS equals dH minus v dp. Those are the two TDS relations. So let's take one of these relations. The first one, this is the second one. Let's take the first one. TDS equals du plus p dv. And I'm going to divide this equation entirely by t. We can get ds equal to du over t plus p dv over t. Now, for ideal gases, we learned that du equals cv dt, and actually cv is a function of t, right? Cv is a function of t for ideal gases, only ideal gases, and we can substitute that into du. So we can say that ds equal to cv dt over t, right, plus p dv over t. And also we know that for ideal gases, pv equals RT. Now, this is in the version of another version of ideal gas equation. In this case, this is specific volume. Where it comes from is that we already know that PV equals MRT, right? So what I'm doing is I divide this both sides by M, right? And this is actually specific volume, PV, volume per unit mass, RT. Now instead of T, I can substitute with V in here, right? In this equation, I can put, instead of T, I can put ds equal cv dt over t. Instead of v, instead of t, erase that. Instead of t, I can put pv over r, right? Pv over r, I can put p dv, and instead of t, I can put pv over r. Now p cancels to p, and r comes in the numerator, v dt t, yes, and this plus r dv over v. Now I can integrate to find the change of entropy. 1 to 2 ds equal integration 1 to 2 cv, it's a function of t, over t dt over t, plus r is anyway a constant, we can put r outside, and then 1 to 2 dv over v. So this I can write 1 to 2. So I can simplify that. This is S2 minus S1 equal to 1 to 2 CV of t dt over t plus r, and this is natural log of V2 over V1. In this case, you can write either specific volume or total volume, doesn't matter, but I would be consistent. I would put specific volume V2 over V1. So that's our first entropy change equation, right? Now to use this equation, we have to know CV as a function of t. Then we can divide that by t and solve the equation. Now if we use the second TDS relation, so the second TDS relation is this. We use the second TDS relation. I can write, I'm going to take another page here. I can write TDS equals DH minus VDP and I'm going to divide by t the entire equation, dH over t minus VDP over t. Now as you know that dH is equal to Cp dt, and by using PV equals RT equation, T is equal to PV divided by R, right? And then this ds is equal to that entropy change Cp, that's also a function of t, dt over t minus V dP. Instead of t, I can put PV over R, right? Now V cancel to V, and then R comes up top. CPT dt over t minus R dP over P ds. Now I can integrate this equation. ds 1 to 2 equals 1 to 2 Cp t dt over t minus 1 to 2 R dP over P. Now this is going to be S2 minus S1 on the left hand side, and then we cannot still solve this part, the second term, first term on the right hand side, right? Still don't know what the function of Cp in terms of t, so we just leave that the same. Minus R can be taken out, and then dP over P is natural log of P2 over P1, right? So that's the second equation. So now we have two different equations to find the entropy change of an ideal gas. First one is S2 minus S1 equal 1 to 2 CVT dt over t minus, so plus R natural log of V2 over V1. The second one, S2 minus S1, 1 to 2 CPT dt t minus R natural log of P2 over P1, P2 over P2 over P1. So these are the two equations that we can use to find the entropy change of an ideal gas. Now, since we don't know what are the relationships of Cp and Cv in terms of T, we're going to use two different methods. One of these is called the constant specific heat analysis. In this case, we consider Cp and Cv are constant. Cp and Cv are constant at the room temperature, at a given temperature, or at average temperature. Okay. And the second one is called the variable specific heat analysis. Variable specific analysis or exact analysis, right? So the first one in blue, it's approximate analysis. This is called exact analysis. In this case, we're going to use a different method, which we have to use a table. In this book, in Sengel and Bowles, you're going to use table A17 for that case. Okay. So let's see how we're going to change these two equations to obtain the equations for constant specific heat analysis and variable specific heat analysis in the next video. Thank you very much for watching.